You're 1 in a million. $1,000,000. You have one chance in a million.
Yeah, people use that all the time, don't they? They say those things. And yet people, I don't think, have any idea how much a million really is. And that's what you and I are going to find out today. Okay. First of all, here is a box of sugar cubes. See how many are in there?
252 cubes.
Okay, now to find out how many cubes would make a million in boxes like this, what do we have to do?
Divide 1,000,000 by 252.
Okay, you do it on the calculator. I'll put it down here.
1,000,000 divided by 252 equals 3,968. That's a lot.
Yeah. Almost 4,000 boxes, right?
Yeah.
Well, how big a stack would that make now? First of all, you have to figure out the height of one, right?
Right. Here. It's 5 centimeters.
Okay, so what do you have to do?
Multiply by 5 equals 19,841
centimeters. We'll put cm. How many meters?
That would be
2 spaces, right?
Yeah. 198 meters
tall. That's how many boxes. And we'll go outside later and take a look at how really tall that is.
Okay.
Now, the next problem is, if we took sugar cubes and lined them up to get a whole million in a line, you'd be surprised how long that is. Take the calculator and come around over here.
Okay.
Because here is 1 sugar cube. Here, give it here. I want you to measure the length of 1 sugar cube.
1.5 centimeters.
Okay, now I have the first 10, see? Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have the last 10. You see the last 2 numbers? What do they read?
999,999 and 1,000,000.
Okay, now in order to get a million between these two, we have to put them a certain distance.
Yes.
That's what we're going to calculate.
Okay.
Okay? I'll take the front numbers, you take the back numbers, and let's go find out what a million is. How tall was this stack of boxes?
198 meters.
That's from the top of the tower all the way down to the ground.
That's a lot of sugar.
Sure is. Now, the other thing we were going to do is actually line up 1,000,000 of them. So here, put this one down at the base of the tower. You've got the first 10, right? Like that? And I want you to calculate how far we have to go to put the millionth one way down out someplace. But we don't want to leave that here in the ground. Somebody will step on it. Just remember, it's at the base of the tower, okay?
Right.
Okay, each sugar cube was how long?
1.5 centimeters.
Okay, multiply by 1,000,000.
Is 1,500,000.
Okay, now change that to meters. What do you have to do?
Divide by 100 would be 15,000.
Okay, and now to go to kilometers?
Divide by 1,000, and that would be 15.
Okay, so we got to go 15 kilometers. I'll keep an eye on the odometer, and I'll let you know when we get there, okay? Okay, all clear, come on.
We sure have come a long way.
Sure have. Okay, you put it right down there.
That's 15 kilometers.
You're right. You need 1 more sugar cube. There you are.
That's 1,000,000 sugar cubes.
Yeah,
that's a long way.
From here all the way to the tower. You see it there?
Yeah. It's the one right to the left of the tallest building.
Right, the tall building, then right to the left. Okay. Imagine sugar cubes from here all the way to there. As a reward, you can have one.
Thanks. Now there's only 999,999.
Right. Aaron, all I have to do is pour a little water into this funnel, and you watch what happens.
It's coming out again.
Yes. I have a perpetual motion example.
That can't be true. There's no such thing as perpetual motion.
Well, the water that seems like it's going in here is coming back down and going all the way uphill, which you know you can't do, right?
No, you can't.
There must be some kind of force. Well, I call it a mystery fountain. You can see why. And I've covered the two bottles with cardboard so that you can't see what's going on. Because I think once I uncover it, you will be able to solve the mystery. First, this one. You start tracing what happens to the water from the funnel.
Okay. The water comes into the funnel, and then it goes down
into the long
water,
tube.
in the long tube. And
Now,
then,
what happens to the air here?
oh, the air is getting pushed on by the water,
Right.
I guess.
Pushed up, really,
Yeah.
going through the small tube.
Yes, it goes up through the small tube and around and out again through the small tube.
Right.
And there, I guess it would be the opposite. The air is pushing on the water so
Right.
that the water goes up this
The
tube.
long tube, and trace
then
where it ends up.
tube. Hey,
Back
it
at the
goes
funnel
back
again.
here
So how long is this perpetual motion machine going to continue?
until we run out of water or run out of air.
Right. We're going to run out of water here pretty soon, and that will be the end of it. Then all we have to do is switch the two bottles, and we can start all over again. And is it ready? As soon as we get down to the level, you'll see bubbles coming up, and there we go.
There it
That's
goes.
the end. Okay. Now let's switch them.
Okay.
Keep the stoppers at the same position, but just switch the bottles.
There's a lot
Okay.
of water in here.
Okay, would you like to start the perpetual motion going?
Okay.
Now notice, by the way, I've given you red water
It's red.
so that you can see that the water that goes in there is not the water that comes out here, which is
Okay.
obvious. Go ahead, start it just a little bit to get it going. Here it comes. There it goes. Now trace it
Okay.
from the funnel.
Okay, the red water went in here, and it went down through the long tube to the bottom.
So what are we adding to this one?
We're adding water, and it's pushing the air out.
Right.
That goes up through this short tube.
What
and
are we adding to
around.
this one?
We're adding air.
To that one. So what are we getting rid of?
We're pushing down on the water, so it goes up through the longer tube
Okay.
and around
Okay.
and down through the funnel again.
Okay. So while I call this a mystery fountain, I can't call it that any longer, right?
No, it's no
Because
longer
you've
a
solved the
mystery.
mystery. This snapshot by Gordon Rhoda of the University of Arizona dramatizes how the island of Guam is being overrun by brown tree snakes. They probably arrived in cargo ships and, with no natural enemies, have multiplied and to date have destroyed all the forest birds, 3 species of bats, and a variety of lizards. The snakes even invade people's homes. They're poisonous, but no deaths have been reported. There's no easy solution to one of the most severe examples of native wildlife being destroyed by an imported species, the brown tree snakes. Notice you can see the light that I've got shining on the spoon,
Yeah, you can.
but not in the water.
No, you
Okay.
can't.
Now I'd like you to add some powdered milk, about half a teaspoon or so.
Okay, sure.
Okay, and then stir it up. See any difference?
Well, yeah, you can, the water is cloudy, and then you can also see the light in the
Yeah,
water.
you can now see the light beam very easily. That's because you made a colloid. Have you ever heard of a colloid?
No, I haven't.
C-O-L-L-O-I-D. Well, let me see if I can explain it. You know about a solution?
Yeah.
Okay. What is a solution?
Well, a solution is where 2 products are mixed together to make one other product.
Right. And in that case, it usually means that molecules of one material go all the way through another material, and we're using this marble to represent that kind of a molecule.
Okay.
Now, you know about a mixture. What
Yeah.
is a mixture?
Oh, a mixture is just 2 things mixed together,
Right.
and they can separate or
They-
they could mix.
Right. In this case, we'll let that ball represent like a grain of sand. If you mix sand and water, the sand all sinks
Yeah.
to the bottom. Well, there's a whole bunch of particles that are in between that, and they're called colloidal particles.
Okay.
And they stay suspended. They don't sink to the bottom like sand, and they don't dissolve like a solution. In fact, that's what you made. You see it?
Okay.
You made a colloidal suspension of a solid in a liquid.
Oh, okay.
Now you can also have a liquid suspended in a liquid. In fact, here's an example right here. Here's water. Let that represent vinegar.
Okay.
And here is salad oil. You mix vinegar and oil together to make a salad dressing, right?
Yeah,
pour a bunch of vinegar in there.
Okay. About that much?
Okay, that's good enough, just so you see that it all comes to the top, right?
Yep, except some of the stuff that's stuck along the wall here and on the bottom.
Then, now we'll add powdered mustard, because the little tiny particles of them, I'll add more than you would if you were making a salad dressing.
Yeah.
Now put the top on and shake it up.
Okay.
Okay. See the difference?
Well, yeah, there's foam on the top, and the water seems to be like a yellow murky.
Yeah, it's all cloudy because we now made a suspension of the oil, little tiny globules of oil connected to one of the little pieces of mustard.
Okay.
And they stay suspended.
Oh, neat.
Okay, here's another example. Oil and water not supposed to mix, right?
Well, no,
There's-
not that I know of.
There's oil, motor oil.
Okay.
Put some of that in there just like you did before.
Okay, sure. About the same amount?
About the same amount, right. Okay. This time put the top on and shake it up first.
Okay, sure.
Okay, it looks like it might be a colloidal suspension because it's sort of cloudy.
Does.
And you've broken up the oil into little tiny droplets, but look what's
Yeah, you
happening
can
to
see
them.
them.
Yeah,
They're all floating to the
They're
top.
going to float to the top. And eventually it would all get up there. How do you get rid of oil when you wash your hands?
Well, you use warm water and soap.
And soap. And the soap makes a colloidal suspension out of the oil. Here's
Okay.
some soap. Put it on there and shake it up just like you did
Alrighty.
before.
A little more, or is that enough?
That's okay.
Okay.
There you made a colloidal suspension of the oil in water. And if some of it comes up, means you need to add more soap. You
Oh,
probably
like
need to
this,
add a
the
little
foam
more.
and then the
Yeah,
oil, and then
right.
it looks like it's clearing up
Okay,
to
so
the
now,
bottom.
this is an example of a liquid in
Okay.
suspension in a liquid. Now we need a gas suspended in a liquid.
Okay.
Go to the refrigerator, and on the bottom shelf you'll find some stuff. Bring one of them up.
Okay, sure.
You recognize that?
Well, yeah.
You know what to do with it?
Yeah.
Okay, go ahead, shake it up. And this time, release the entire contents of the whipping cream in the glass.
Okay.
Because this is an example of a colloid called a foam.
Okay. Well, should
Okay,
I finish
that's the end of
everything?
it?
No, there's a little bit more,
Okay.
not much.
Okay,
That's it.
that's one kind of foam, which is edible, I assume. Do you want to try it? I
Sure.
cleaned out the glass so we could have.
It's good.
That's your last taste, because here is another example of a different kind of foam.
Okay.
You know what it is?
No, I
Shaving
don't.
cream.
Oh, okay.
Okay, try, see if you can go all the way around with the shaving cream.
All the way, like, around
Yeah,
it?
all the way around it. Down below.
Oh, down below
Down
here?
below, yeah, because you're going to fill it all up.
Geez, it looks almost better to eat than the whipped cream does.
Doesn't it, though?
Looks so foamy and good.
Right. Now, there's an example, however. Keep going, just see if you can empty the whole thing. An example of gas suspended in a liquid, which scientists call a foam. I don't know if you've ever emptied a whole can of
No, I
shaving cream
haven't.
before, but keep going. Because it's a good example of that whole class of substances which we call colloids. When you realize that humans have explored so many places in outer space, you may be surprised that there are unexplored regions of inner space on Earth. This is one of them, the bottom of Lake Superior.
Michigan State University, in cooperation with government agencies and other institutions, explored the bottom of Lake Superior with the research ship Seward Johnson and its 4-person submarine. Here are some of the expedition's surprises. Much of the bottom was barren and featureless, like an underwater desert. But there are indications of living things. In the lower right-hand corner, a small fish produces a cloud of mud. The depression in the bottom may have been formed by the fish for nests or hiding places. Trenches in the bottom puzzled scientists until they saw that a fish digs them. The submarine lights disturb the fish, and it uses its tail to dig deeper into the trench. This cliff looks like it was carved out by a knife. Scientists speculate that it too was produced by the motion of fish. They discovered these ragged cliffs near the deepest part of the lake. Scientists have no idea what geological processes formed them. So now we have traveled to one of the unexplored regions of the Earth's inner space, the bottom of Lake Superior.
Say, Mr. Wizard, aren't the candles supposed to be burnt out by now?
Well, you'd think so because they're burning down to the level of the water. You'd think the water would put them out. But think about this, Ben. As the candle burns, it uses up some of the wax in the candle. So it's going to float a little higher. In other words, the candle keeps getting shorter and shorter and shorter as it floats on the surface of the water. So it'll burn to practically nothing. See this one over here?
Yes.
It's been burning for 15 minutes and still isn't out.
Whoa.
The secret is to get the candle to float upright.
Oh.
And here's how I did it with mine. You want to light the candle over there first?
Okay.
Okay, here, I'll take the match and put it in my... What I'm going to do is to heat pin. Now, you can use tacks, thumbtacks, or regular tacks, all kinds of various weights, usually that you can hold in the candle flame to get it nice and hot, and then put it over in the candle and stick it through it like that and hold it until the candle wax solidifies again, and it'll hold the pin in place.
Okay.
Like that, see? Let's say you can use thumbtacks or various other things. I found it takes about 3 of them to hold a candle about that size.
Okay.
Then put it, I'll move this one out of the way so you can see. Okay, I just put that one out. Now, when you put it down in the water, you try to not let the wick get wet. Okay?
Okay.
Here, take a match and see if you can light my new floating candle. There you go. Now, so you understand the secret. If you want to have a centerpiece or something on a birthday party in which you can sort of astound everybody with floating candles that don't go out, weight them with pins or tacks or something at the bottom so they float upright, and you can have floating candles.
That's great.
Thank you.
What's this? Not a formation hanging from the roof of a cave. In fact, they're seeds. While it's true you often eat the seeds of fruits and vegetables because that's where a plant often stores food, in this case, you discard them as you cut up the outer cover of the seeds of the green pepper.
Brenna, here in this little vial is a radioactive liquid. And this detector is picking up the radioactivity and sending a signal over here to the computer, and we've recorded all the radioactivity that's coming off of that. See? Notice it started here at 60. And you are going to be able to identify that chemical by its characteristic half-life. Have you ever heard of half-life?
No, I haven't.
Well, here's I drew one up, sort of a theoretical one. And see, here it started at 100. Now watch what happened at the end of the first time interval.
It went halfway to 50%.
Right, to 50, half-life, you see. Now what happened at the second hour?
Well, halfway between 50 is 25, so it went to
Right.
25. And then it keeps going half of...
And in this case, I only did it for 4 time intervals, right? Okay, now, scientists have measured the radioactive half-life of a lot of different materials, and here are some of the most important ones. Have you ever heard of any of these?
Yeah, some of them.
Uranium-238, yeah. Notice its half-life?
4.5 billion years.
Yes. Okay, what is the next one?
Carbon 14, 5,930 years. Cobalt 60, 5.26 years. Iodine 131, 8.04 days. Bismuth 212, 60.5 minutes. Barium 137, 2.6 minutes. Radon,
Radon, that is.
Radon.
Yeah, radon.
220, 51.5 seconds.
You notice how I arranged them?
Oh yeah, it goes from the longest time to the very shortest
And
time.
when you say longest time, you really mean longest, 4.5 billion years, all the way to seconds. And some of them even last longer than that. You've heard of carbon-14. They use that for dating things. Cobalt-60 is also used in medicine. So is iodine. So is bismuth. Barium. And radon, is you probably have heard it's supposed to be coming out in people's basements and whatnot. Yeah? It's a radioactive material. Okay, well, from this list now, you should be able to identify what that radioactive material is. It started at 60, right?
Yeah.
Okay, how do you figure its half-life?
Well, the half-life of 60 is 30.
Yeah.
And then you go across from 30, and it's just a little bit before 3 minutes.
Just a little before 3 minutes. Okay, what radioactive material is it?
Barium 137.
How do you know?
Because 3 minutes is the closest to 2.6 minutes.
Right, yes. So very good. You were able to identify an unknown radioactive material by identifying it by its half-life. Congratulations.
Thanks.
I don't know, have you ever taken pictures with a camera like this?
Very similar, yeah.
Yeah, with a shutter speed that you can adjust the shutter speed. Well, what if you took it to your camera shop because you didn't think the shutter speed was accurate? They might use a gadget, something like this, to actually check it, and that's what you're going to do. First of all, this is a counter that can count in thousandth of a second. Take that piece of paper out of the way so the light can go from there to there and start the counter. Watch.
Oh, it starts counting.
You see, it's how it's starting, yes.
And then you put it in and it stops again.
And then it stops again. So push the reset button.
Okay.
And now I will set the camera, I've got the camera shutter set at a 60th of a second. So I'll put it in place like this, and you hit the reset button.
Okay.
And now I'll fire the shutter and see what we get.
Decimal 0.16.
Okay, hold it there now. Decimal 0.16. That's in thousandth of a second, yet the shutter speed is in a 60th of a second. Can you transfer fractions to decimals?
Yeah.
How do you do that?
What you do is you take the denominator and divide it into the numerator. Which
Okay,
is
in
the
this
top
case?
number. It would be 1 divided by 60
What do you get?
equals 0.017. So it's pretty close.
Yes. So the camera is probably working pretty well. At a 60th of a second. Okay, I'm going to take the camera out of the way because I now have another test. Put the cardboard in place. Here, take the cardboard and I'll set the reset button. And now see how fast you are. Well, pretty slow by cameras.
Yeah.
Faster than a 60th of a second. Try.
That
See
was
if you
better.
can improve it. Ah, there you're getting a little better.
Yeah.
Anyway, you see now how a very high-speed counter can not only check shutter speed, but check your reaction time, too.